2 champions, welcome to day 4 of 21 days challenge to get 95% in second PUC board exam. So as part of this challenge today, I have given you 2 chapters for homework, current electricity from physics and coordination compounds from chemistry. So you have to revise these 2 chapters and practice its most important questions from the PDF I have provided. If you haven't downloaded yet, the link is there in the description section. Please go there and download it. So by this time, I hope all of you have completed the challenge. If yes, let me know in the comment section by putting yes ma'am, day 4 completed, or whatever is your level of your progress. Do let me know in the comment section so that I can know whether this challenge of 21 days is actually helping you or not. So now in this video, I will be discussing the most important MCQs from the chapter coordination compounds, and these MCQs are taken from your question bank. Okay, so let's get started and see the first question here. The first question is from the Werner's theory that for each mole of PdCl2.4 NH3 gives 2 moles of AgCl on reaction with excess of AgNO3. The secondary valency of the metal is. Now 2 moles of AgCl is formed. That means there will be 2 moles of chlorine outside, right? So you will have PdNH3 whole 4 Cl2, right? So 2 moles of chlorine are present outside. That means 2 moles of AgCl will form. So the secondary valency of the metal here you can see is 4. So that is why option number D here. Next, the conductivity of COCl2 NH3 whole 4 Cl in a solution corresponds to. So what will happen? This will form one particular cation and this one will form one anion. So there will be total 2 moles. That is option number B here. Next, which among the following has the highest molar conductivity? So highest molar conductivity depends on the number of ions produced, right? So here you can see 4 potassium and one particular complex is there. So 5 ions will be produced here. Here you can see this whole complex will be 1 ion and 3 chlorine are there. So total 4 ions here. Here you can see 1 complex and 1 sulfate. So there is 2 ions and here you will have 1 ion. Okay. So now if you totally count, this is having the maximum number of ions. So it will have the highest conductivity. So option number A here. Next is the primary and the secondary valency of FeC2O4 whole 3 minus complex R. Okay, so here you can see that the primary and the secondary valencies of Fe we have to find out. So secondary valency is obviously this is a bidentate ligand, means each C2O4 forms 2 bond. So 3 C2O4 will form 6 bond, right? Then you have Fe oxidation state. If you see X minus 6 is equal to, so this is plus 3. So 3 and 6, that will be your option number B here. Next, which of the following octahedral complex has least conductivity in the aqueous solution? So for least conductivity, you have to assume here that cobalt complexes generally have a secondary valency of 6. Okay, so that means what we will have cobalt here. So if I want to have 5 chlorine or any 6 ions you take, so inside there will be 2 chlorine, outside there will be 2 chlorine. So total number of ions produced here is 3. Now if you see here also 4, 5, 6. So if I just write down like this, CO NH3 whole 4, okay, and then I have to take 2 chlorines and then 1 chlorine outside. I have to maintain the secondary valency of 6 for cobalt. So you can see total number of ions produced here is 2. Now here if you see, I have a CO NH3 whole 6 and then Cl3. So total number of ions here produced will be 4, and here we have Ma3B3. So this whole will be one complex, that is CO NH3 whole 3 and Cl3. Okay, so this is 1. So if you see the total number of ions, the total complex with least conductivity, that is your 1. So option number D here. Next, the compound does not give the test of sulfate ion in aqueous solution is. Does not give test for sulfate ion. So you can see this one will give test for sulfate ion, this will give test for sulfate ion, this one will also give, but yes, this one will definitely not give the test for sulfate ion because it is inside the complex. So option number D here. Next is when a complex K4FeCN6 is dissolved in water, it dissociates into. So you can see it will give you 4K plus and 1 complex here. So that will give you 4K plus and 1 complex. That is your option number B here. Next, a purple compound M has a formula of CONH3 whole 6 Cl3. On addition of excess of AgNO3 to form 1 mole of compound M produces 2 moles of AgCl. If the secondary valency of cobalt is 6, then the correct formula of the complex will be. The secondary valencies of this one is 6. So I will have CO NH3 whole 6. Okay. Then there is, you can see that the total number of moles of AgCl formed is 2. That means only 2 chlorine I can have outside. That means 1 chlorine has to be inside, then NH3 will be 5 and 1 NH3 has to be outside. So the formula that matches this one is option number C. Which of the following is not a double salt? Potassium ferrocyanate, that is your complex, so it is not a double salt. Next, the correct order of stoichiometries of AgCl formed when AgNO3 in excess is treated with the complexes given here, right? So you can see that 6, we have to maintain the coordination number of 6. So 6 NH3 will be there, 3 chlorine will be outside, so 3 moles of AgCl will form. Now 5 NH3 and 1 chlorine will go, so total there will be 2 chlorine outside. So that means after 3 there will be 2 moles of AgCl, and then you have 4 here and 2 chlorine, so 1 mole of AgCl will be, so option number B. In complex compounds, the metal atom or ion acts as, now metal atoms gain electrons, right? So when they gain electron, they behave as Lewis acid, so option number A. The complex PtCl2 4NH3Br2 is treated with excess of AgNO3 solution, 2 mole of AgBr is precipitated. The primary and the secondary valency of this complex is, okay, so now if you see 2 moles of AgBr is precipitated, so that means the complex will be something like this: Pt Cl2 NH3 4, okay, and you have Br2, right? So now if you see here, the primary valency here will be the oxidation state of platinum, which is number 4, and the secondary valency is 6, right, because the total coordination number is 6. So 4 and 6, that is option number C. Next, when 1 mole of PtBr2.4 NH3 is treated with excess of silver nitrate solution, 2 moles of silver bromide is precipitated, okay. Then the primary and the secondary valency of the complexes, I think this is similar to this one. So you will be having the complex like this: PtNH3 whole 4 Br2, right? Now if you see the oxidation state, you have to first find the primary valency, right? The primary valency is 2 here, and the oxidation state or coordination number is 4, so 2 and 4, that is option number D. Coordination number of the central atom is determined by only the number of sigma bonds formed by the ligand and the metal, so option number C here. Next, in the complex ion FeC2O4 3 minus, the coordination number of Fe is, okay, so you can see Fe will have 6, each C2O4 will form 2 bonds, so 3 will form 6, so that is why option number B here. Next, on treating 100 ml of 0.1 m aqueous solution of complex CrCl3.6H2O with excess of AgNO3, 2.86 gram of AgCl was obtained. The complex is, now if you see here, 2.86 gram of AgCl is formed. Then that means how many moles of AgCl will be formed? So you can just calculate the moles of AgCl. So the given mass is 2.86, molar mass is nearly 143, okay, 143.5, but I'm taking it as 143. If you divide, we'll get 0.02. That means 2 chlorine should be present outside to get 0.02, because here if you see, this is also 0.01 mole if you multiply it, right? So if you see, number of moles is what? Molarity into volume by 1000. So molarity is 0.1, volume is 1000 volume is 100, and this is 1000, okay. So it is 0.01, right? We will get 0.01 here. So that means 2 chlorine has to be outside. This is not possible, this is not possible, this is not possible, this structure is possible, so option number B here. Next, the complex hexaamine platinum 4 chloride will give number of ions on ionization, okay. Hexaamine platinum 4 chloride, so you have Pt NH3 6 Cl, okay. So here it is, okay, so you have to calculate here. So Pt hexaamine platinum 4 chloride, right? So here it is 4 plus and this is minus, so this one will be multiplied here, this one will be multiplied here. So we will have the actual formula of complex like this: Pt NH3 whole 4 and this one Cl4, right? So total 5 ions will be produced, option number A. The coordination number of Fe and cobalt in the given complex is, C2O4 will have 6 coordination number and SCN will have 4 coordination number. So 6 and 4, which is option number C here. Next is, out of the following compounds, which of the following will have the minimum conductance in the solution? For minimum conductance, you should have least number of ions, okay. So for that, if you see, here also 1 ion is produced, here also 1 ion is produced, here 4 ions will be produced, okay. So that is why both A and C, that is option number D. Now cobalt 3 chloride forms several octahedral complexes with ammonia. Which of the following will not give a test for chloride, okay. Not give a test for chloride means it should be inside the complex. So here octahedral complexes means it is having coordination number of 6. So here the molecular formula should be like this: H2O whole 6 Cl3. So 4 ions will be produced here. Now here we will have H2O5 Cl and Cl2. So here 3 ions will be produced. Here I will have COH2O whole 3 Cl3, and here I will have COH2O 4 and Cl2Cl, right? So that means what will happen, you can see that here there is only one ion, so minimum conductivity, option number B here. Next question is match the following match the coordination number and type of hybridization with the distribution of hybrid orbitals in the space provided on the valence bond theory. So if you have coordination number 4 and type of hybridization is sp3, then the distribution of hybrid orbitals, it will be in the tetrahedral geometry, right? So one will be R, so I can eliminate these two. Okay, next is dsp2 is square planar, so 2 has to be S, so I can have only this particular option. Okay, but I want to just highlight this one. Please remember that this question answer given in the answer key is actually wrong. Okay, I'm just putting a circle here. This question is given wrong. Answer given for this one is option number B. Okay, but the correct answer is option number D. Okay, please remember. Next is we'll move to question number 22 here. So question number 22 is NH2 CH2 CH2 NH2 is a ethylene diamine bidentate ligand, but it is also chelating ligand because it forms a circular complex. So option number B. Which of the following is true about the 3D series and EDTA complex? So you know one metal forms or bonds with one EDTA, so it is a 1:1 molar ratio of option number D. Which of the following is a homoleptic complex? So you can see here this particular part, ammonia, is having all the same ligand, so it is a homoleptic complex. Metal isothiocyaneto will have NCS bond. Okay, thiocyaneto is SCN, isocyaneto is NCS, so that is option number A here. Next is donor atom of EDTA is you have N and O. Okay, so that is option number A. Ambidentate ligand is where you can both the atoms can donate, so that is option number B. The ligand which forms more stable coordination, so it is always your polydentate ligand, so it has to be option number B. Okay, but in this particular question, again I want to highlight, answer given is wrong. Answer given is actually CN. Okay, but the correct answer will be option number B. Just I am telling you so that you should be careful. Okay. Next is the counter ion in the particular complex. Here it is chlorine, so option number C. Next is which of the following complex does not have a chelation? So this is a polydentate ligand, this is also polydentate ligand, this is also polydentate ligand, this is a monodentate ligand. So here there is no chelation, so option number D. Which is the most stable complex among the following? Again, for stability you need chelating ligand, so this is a chelating ligand, so option number C. Next, match the following ethylene diamine. It is a bidentate ligand, so A has to be P. There is three options. I can eliminate this one. This is an hexadentate, so B is S, right? So yeah, option number C is the correct answer. Next is a ligand which has two different donor atoms and either of the two ligates with the central atom in the complex is called as, it is your ambidentate ligand. The homoleptic complexes among the following are, you can see here it is homoleptic and here it is homoleptic, A and C, that is option number D. Then ethylene diamine tetraacetate, EDTA, okay, it is a hexadentate ligand, so option number C. Next is which of the following is not an ambidentate ligand? SCN is ambidentate because both S and N can donate. C2O4 is not ambidentate because it has only oxygen as the donor atom. Okay. Next, here also I just want to highlight answer given is wrong in the answer section. So 36 question, A given is the answer, but the correct answer is option number B here. Next, moving to question number 38, statement based question. Okay, just a minute. Okay, statement based question. CONH3 6 is homoleptic, whereas this one is heteroleptic. Yes, that is a correct statement because here you can see all the ligands are NH3. Here we have mix of two ligands. Complex, this one contains only one kind of ligand, but this one contains more than one kind of ligand. Yes, both the statements are true, so option number D. Next, homoleptic complexes from the following complexes is, you can see diamine chlorido, so this is not a homoleptic complex. Potassium trioxalato, yes, this is a homoleptic complex because we have only oxalato ligand. Here you can see triamine and aqua, two ligands are there. Pentaamine and carbonato, again two ligands are there, so option number C. But this answer also is given wrong in your answer key. So the answer that has been given here is option number A. Okay, option number A is given, but the correct answer will be option number C. Okay. Now moving to the next question, a chelating ligand has two or more than two donor atoms to bind to a single metal atom. Which of the following is not a chelating ligand? Oxalato is a chelating ligand. This is also chelating ligand. This is also chelating ligand. Thiosulfato has only one unidentate ligand, so it is not a chelating ligand. So option number A. But this answer is also given wrong in the book in the answer key. So okay, I'm highlighting answer they have given is C. Okay, but this is not a correct answer. Now we will move to nomenclature. The IUPAC name of the given compound is, okay. So you can see it is potassium and trioxalato. So I have potassium trioxalato since it is a negative charge anionic complex. So chromate 3, option number B here. Just change the color. Yeah. Next, the IUPAC name of the complex CuNH3 4SO4 is. So you can see that I have tetraamine here and copper. Copper charge is definitely 2 and sulfate. So option number C. Okay. Next, we have the IUPAC name of the complex NiNH3 6Cl2 is. So here it is hexaamine nickel 2 chloride. So option number A. Okay. Next is the formula of the complex tris ethylene diamine cobalt 3 sulfate is. You have to write the formula of the complex. So tris ethylene diamine means you should have 3 EN groups. So that is present in all of them. And sulfate should be outside, right? So here sulfate is inside, here also sulfate is inside. So we'll remove that. And if you see the complex cobalt 3 plus 3 will be, so you can see that this particular complex will have En3 and here I have plus 3 and SO4 is having 2 minus. So if I multiply, I'll get this compound. So option number D. Which formula and its name combination is correct? Okay. Diamine chlorido nitrito N platinum 2. Yeah, this is correct. You have asking about incorrect. Okay. Next, dichlorido bis ethane 1,2-diamine cobalt 3 chloride. Okay, that is also correct. Next, here you can see next one is potassium trioxalato chromate 3. That is also correct. Pentaamine carbonyl. Okay, carbonyl is incorrect. This is actually carbonato, right? So this name is wrong. So option number D here. Next, moving to question number 45. Which formula and name combination is again incorrect? You have to find out. Potassium trisoxalato aluminate. This is a correct name. Then you have diamine chlorido nitrito and platinum 2. This is also correct. Then we have tetraamine aqua. Then we have chlorido cobalt. Then we have 3 chloride. This is also correct. Then we have dichlorido. Here you can see di is given. It has to be bis ethane 1,2-diamine. So this is incorrect. So option number D is the correct answer. Next, the correct answer for cisplatin. Cisplatin structure is PT. You have NH3, NH3, and you have Cl and Cl. Okay, that is the structure of cisplatin. So I will have diamine dichlorido platinum 2. Okay, so diamine dichlorido platinum 2. Yes, that has to be the correct answer. Here it is 4 and here it is 0 and here it is diamine dichlorido platinum 4. Yeah, these two options are I think same. No, okay, dichlorido is written first, so this is also incorrect. So option number A is the correct answer. But here also the option given in the book is wrong. Okay, 46 question. The answer given in the book is B, which is book means I'm talking about answer key. That is wrong here. Okay. Next, moving to question number 47. The IUPAC name of the given compound. So you can see it is first of all pentaamine should come, then carbonato, then cobalt, and the oxidation state is 3 and chloride. So option number C should be the correct answer. But the answer here given is also wrong. The answer given here is A option, okay, which is completely incorrect. Okay, moving to the next question 48 here. The formula of the penta aqua nitrato chromium nitrate is, okay, penta aqua, first of all 5 aqua is there, then nitrato is NO3, okay, then we have chromium and nitrate. So yes, this is the correct structure. Next we will have in the complex the ligand shows linkage isomerism. So for that we need to have 2 ligands. So it is NO2 minus, both N and O can form bond here. PTNH3 4 Cl2 Br2 complex can show. So here you can see this can show actually cis and trans isomerism, okay, and it can also show ionization isomerism. So we have ionization and geometrical. So option number B here. 51, the possible isomerism in complexes this and this respectively are. So here actually answer can be both B and D. Okay, so if you see this particular complex MA3B3 type, it can show geometrical as well as linkage isomerism because NO2 is present, and this particular complex can show linkage isomerism because NO2 is present, and with chlorine it can undergo ionization isomerism as well. So geometrical, linkage and ionization, all of them are correct. So geometrical and linkage is here, the linkage and ionization is there, so both B and D is correct. Okay, but the option that is given correct in the book is option number D here. Okay, next 52, which of the following coordination entity will have a racemic mixture? Okay, racemic mixture means it should have optical isomerism, so trans will not form, and COEN here, that is not there, this one will form, it will have the two enantiomers dextro and levo. Next, the complex, this one is given, are the examples of, so here NO2 is there and here ONO is there, so it is a linkage isomerism example 53. Next, the number of geometrical isomerism MA3B3 type, it has facial and meridonial, so option number 2. Now let's see question number 55. Both geometrical and optical isomerism is shown by. So if you see this particular compound, right, this shows geometrical cis and trans, and the cis form is optically active, so this is the correct answer. Here only optical isomerism is there, no geometrical isomerism. Here no isomerism is there, here only geometrical isomerism is there. Okay, in the reaction of this one with this one NH3, two isomers of product are obtained. The initial complex which is formed is always a cis isomer. Okay, so option number A here. Which of the following is not a subdivision of structural isomerism? Geometrical isomerism is not a subdivision. Option number D. Square planar of MABXL have two cis and one trans form. Which type of complexes shows geometrical isomerism? MX4 tetrahedral doesn't show geometrical. Square planar where all the ligands are same will not show, tetrahedral will not show. So option number C is the correct answer. But here the answer given is incorrect. Okay, for 59 the answer actually given is D. Okay, this is the answer given, which is completely wrong. Now moving to the next question, that is 60. Which type of complexes doesn't show geometrical isomerism? Again similar, tetrahedral you can eliminate. Okay, these two questions. Okay, does not show, right? So square planar will show, octahedral will show, and square planar will also show. So this is 60A, which is option number A. Next, the optical active complex is trans one is never optically active, cis form is optically active, so option number B here. Next, the linkage isomerism arises while containing an ambidentate ligand. The type of isomerism arises from the interchange of the ligands between the cationic and anionic complex is coordination isomerism. The complex compounds given here are, so you can see these are all your ionization isomerism, so option number C. Next, here match the compounds COEN whole 3. This one will be actually optical isomer, so one will be B. Okay, so I will have this one and this one. 2 will be coordination isomerism, so 2 is D. Okay, just a minute. CrNH3. Okay, 1 second. One will be optical isomerism, right? Okay, I incorrect. This is wrong. 1 second. So one has to be B. So I can have which options available? I can eliminate option number C and option number D. Okay. Now 2 will have coordination. So 2 is D, which is present here. So A is the correct answer. This one will be your linkage isomerism because here I have an ambidentate ligand. So 3 is A. And this particular compound will be having your geometrical isomerism. So 4 is C. Okay. So this is actually 3, MA3B3 type. Okay, next, the number of stereoisomers exhibited in this compound. So first of all, stereoisomers means including both geometrical and optical. First cis and trans will form, then the cis one will optically active. So total there will be 3 isomers. Okay. Next is question number 67. Among the following, so if you saw here is a strong field ligand. So this is diamagnetic and this is paramagnetic. So option number A is correct. Next is question number, this one, CONH3 whole 6 is diamagnetic, COF is paramagnetic, that is correct. This is due to, so not coordination, coordination number. So you can see coordination number is same for both, so that is not the reason. Oxidation state is also both, so that is not the reason. Charge is not the reason, it is due to the nature of the ligand. Here it is a strong field ligand, so pairing takes place. Here there is a weak field ligand, so pairing does not take place, right? So the answer to this question is actually option number C, but question answer given in the book is actually option number A, okay, which is again incorrect. Next, moving to question number 69 here. Okay, 69 question is sp3d2 hybridization is present in, it is option number A, COF6 3-, okay, outer orbital complex. But the answer given here is also incorrect. Okay, 69 answer is option number C is given, which is completely wrong. It is D2sp3 hybridization. Next, moving to question number 70, the inner orbital complex D2sp3 is for CONH3 6+. Option number A is correct here. but 70 answer is also given incorrect. I'm just checking which answer is given here. For 70, the answer given is B, which is again incorrect because it is sp3d2 hybridization, means outer orbital. Next is the high spin complex is, okay, just a minute. The high spin complex is what means where you have weak field ligand. So this is not a high spin complex. More number of unpaired electrons should be present. So this is having 4 unpaired electrons, I think. So that is why this is a high spin complex. Tetrahedral complex is NiCl4. Okay, I'll change the color. Yes. Next, square planar is NiCN4. Okay, so if you have already studied the isomers hybridization thoroughly, then these questions you can do very fast. Next, the complex with maximum magnetic moment. Maximum magnetic moment, it should have maximum unpaired electrons. So COF6 3 minus, MnCN6 3 minus, and FeF6 3 minus are. So if you see, Mn is having here +3 oxidation state. That means 3d4. Okay, so 3d4 is there, right? 3d5 4s2. If 3 electrons are lost, then I have 3d4 electronic configuration. So what will happen? 1, 2, 3 and 4. So 1 electron will paired up here. So here the hybridization will definitely be D2sp3. Okay, so this is an inner orbital complex. Now FeF6, if you see, Fe charge is also +5. So this is also D5. But here what happens? Since F is a weak field ligand, there is no pairing of electrons. Okay, all the electrons are present here only. So here the hybridization is sp3d2, which is a outer orbital complex. Okay, so inner orbital complex and outer orbital complex, option number A. The incorrect statement about the valence bond theory is it has a lot of assumptions. It gives quantitative interpretation of magnetic data. It does not explain the color exhibited. So you have to find the incorrect statement, right? It gives quantitative interpretation of magnetic data. No, it doesn't give. So 2 is a wrong statement. And it gives a quantitative interpretation about the thermodynamic and kinetic stability. No, it doesn't give. So 2 and 4 is option number C. Next, the crystal field theory is an electrostatic model. Yes, that is a correct. And ligands act as dipole. That is also correct. So option number A, both the statements are correct here. Next, the degeneracy of d orbitals is maintained when spherically symmetrical field of negative charges surround the metal. Okay, so if you have seen the diagram, first when spherically symmetrical negative charges come, the energy rises, but all of them have the same energy. So that is why option number B here. Next is in complex with secondary valency 6, the set of d orbitals which experience more repulsion is your dx square minus y square and dz square. So that is where they are at the top in the d orbital splitting. Next, arrange the following species in the increasing order of their crystal field splitting. Okay, so if you see ligands, strong ligands will have higher splitting, right? And coordination number 4 has lesser splitting. Tetrahedral has always lesser splitting, so it has to be option number A here. Okay. Next is 81. According to the spectrochemical series, the strongest ligand here is CO. 81 is A. Next is 82, the correct electronic configuration of D4 in a weak field ligand. So if you have like this configuration, D4 means energy is very less, so it can easily go here. So T2G3 EG1, that is option number A. In octahedral splitting, T2G orbitals are actually, they are lowered by how much? -2/5, right? So that means -0.4, lowered in energy by 0.4, that is option number B. Now, if delta O is very large, the correct configuration of D4 system will be, okay, that means here there will be pairing, it will be T2G4 EG0. In octahedral complex ML6, Mn plus have 5 d electrons and L is a strong field ligand. Okay. Next, according to the crystal field theory, the magnetic properties of the complex ion correspond to how many unpaired electrons? Okay. In octahedral complex, Mn plus has 5d electrons. Okay, and L is a strong field ligand. According to crystal field theory, the magnetic properties of the complex ion corresponds to how many unpaired electrons. So if you see, 5 unpaired electrons were present, okay, and there's a octahedral complex, right? So 5 unpaired electrons were present, and in the strong field they will pair up. So now the total number of unpaired electron present is actually option number B, that is only 1, because this will be used because it is the octahedral complex. So we can have now D2sp3 hybridization. Okay. Next, question number 86, the arrangement of ligands in the increasing order of their field strength. Okay, so here if you remember, we have first of all CO is present in all of this. We can eliminate this one. Then okay, here the option which is correct is option number A. Water is OH minus is weaker than water, so option number A here. Next, the magnitude of CFSE can be related to the configuration of d orbitals in the identity as the configuration of, I think we are talking about D4 based on the options. Okay, so if it is less than P, delta O is less, then the configuration is T2G E3G1. That is your correct statement. If the configuration is higher, means delta O is splitting, then it should be T2G4. Again, these all options are incorrect. If ethane 1,2-diamine is progressively added to the green color nickel in the molar ratio 1:1, 2:1 and 3:1, the correct order of the color changes is. So first green is there, then pale blue and then violet. So option number B here. Next is the relation between the crystal splitting energy of octahedral and tetrahedral complexes is delta T is equal to 4/9 delta O. Now see question number 90. Match the coordination compound given in column 1 and the wavelength of light absorbed in column 2. So remember here that if there is a strong field ligand, that means splitting will be more, and if splitting is more, that means it will absorb a light of lower wavelength. Okay. So if you see here that if the ligand Cn is the strongest field ligand here out of all the ligands, so if Cn is the strongest field ligand, means it will absorb the lowest wavelength and highest energy. So that means this will be option number B. So 4 has to be B, which is there in 2 options. I can eliminate the other 2. Okay. Now next one is here purely NH3 is there. So that means next strongest ligand here is 6NH3. So it will absorb the least one here after 310, which is 475. So 3 has to be A here. Okay. Now coming to this one, that is if you see here H2O and Cl. Okay, H2O is a stronger field ligand because 5NH3 is constant. So here splitting will be more, and then this will be absorbing light of least radiation out of these two. So that will be your 500 nanometer. Okay, so 2 will be C and then 1 will be D. So option number C is the correct answer. Next is which of the following statement is true about NiCl4 2-? It has a tetrahedral geometry. That is absolutely correct. Then coordination number of nickel is 2. No, coordination number is 4. sp3 hybridized is correct. High spin complex correct. Paramagnetic is correct. So A, C, D, E, which is my option number A here. And which of the is correct is for COF6 3- ion? It is an octahedral geometry. Yes. Coordination number is 3. No, it is 6. So this is wrong. sp3d2 hybridized is correct. High spin complex correct. So 1, 3 and 4, that is option number D here. Next, if a didentate ligand ethane 1,2-diamine is progressively added to nickel, the following coordination entities are formed, right? Okay. The wavelength in nanometer of the light absorbed in 1 and 3. Now see, in 1 complex and 3 complex, here definitely there is what I'll say, more strong field ligands will be there. So it will absorb light of higher frequency and lower wavelength. So 3 should be, the wavelength of 3 should be less than that of 1. So based on that concept, I can eliminate these two options. I am having these two options remaining with me, where the light absorbed in 3 is lesser than 1. Now, if you see based on the color, okay, so that has to be option number C, because 600 and 535 doesn't match to blue and violet color. So option number C here. Next is, okay, just a minute. Okay, now moving to question number 95 here. Which of the following system in an octahedral has the maximum number of unpaired electrons? So maximum number of unpaired electrons will not be there in low spin. D9 always have only one unpaired electron. D7 high spin, if you see 1, 2, 3, 4, 5, 6 and 7. Okay, so this will have 3 unpaired electrons, and if I have D4 low spin, that means 1, 2, 3 and 4. Okay, so here I have 2 unpaired electrons, here I have 3 unpaired electrons, so it has to be option number C. Okay, next is question number 96. The correct order of wavelength of light absorbed. Okay, so as previously we have discussed, whenever the ligand is strong, it will absorb the lesser wavelength. Okay, here if you see, CN6 will absorb the least wavelength. Okay, because it is having strong field ligands, and least wavelength means highest frequency. Okay, energy is inversely proportional to wavelength. So Cn will be the one with least one. So here I have CO, Cn, Cl, and after that it has to be NH3. Here it is NH3, here it is different. Okay, and after this one, so it has to be option number D here. Okay, 96 will be option number D. Next, which of the following are paramagnetic? NiCl4 is paramagnetic, NiH2 is paramagnetic, and these all complex. NiCO4 is actually D8, but it is not paramagnetic, not paramagnetic, not paramagnetic. So A and D only, that is option number D. But I think this question is also given wrong. The answer that is given is B and E only, but the answer correct here is D. Next, moving to question number 98, the correct order of wavelength of light absorbed by the following complexes is, okay. So first of all, you can see that I have NH3 and CN6. So this one will be having the least wavelength it will absorb, okay. So B will be least, so I can eliminate all these options, okay. B is least here. After that, it has to be A, and here it is A, okay. After that, you can see out of these two, both are water ligand, but this is having least energy, means the splitting is least here. So C will be absorbing the highest wavelength. So BADC, which is option number A here, okay. But this answer is also given wrong in the answer key. Answer given for this one is actually B, okay. I'm marking it here, but it is A. Next is question, which of the following is, I'll change the color, one second. Which of the following are two statements? You have to state correct or false. So CONH3 whole 6 and COF6 are octahedral but differ in their magnetic properties. CONH3 is diamagnetic and COF6 is paramagnetic. So both the statements are actually true. So that has to be option number B, okay. But here also the answer given is actually wrong, okay. Both the statement 1 and 2 are true, that is the correct answer. But here the answer that is given to you is C, okay, but that is wrong answer. Moving to 100th question, the shape of the pentacarbonyl, this is actually square pyramidal, option number A, but question answer given for this one is also wrong. They have given you, sorry, one second. So I'll just correct it. See, the shape of pentacarbonyl iron is actually trigonal pyramidal, okay. Correct answer is C, but the answer that is given to you is your option number A, which is incorrect, okay. Moving to next one, the number of bridge ligands in octacarbonyl cobalt is again 2, so option number A. Number of bridging ligands in Mn2CO2 is 0, there is no bridging ligand, okay. It is two different structures without any bridging. The structure of tetracarbonyl nickel is NiCO4, it is tetrahedral, option number A, okay. Next, next is 103. This answer is also given wrong in our answer key, okay. So the answer that is given in the answer key is actually C, okay. But for a 4 coordination number, you cannot have octahedral, so it is completely wrong. Next, question number 104, Mn2CO2 10 and CO2 CO8 structures have metal metal linkage, yes. Terminal carbonyl groups, yes. Bridging is not present in Mn2CO10. Metal in zero oxidation state, yes. So A, B and D, only A, B, D, which is option number C, okay. But here, okay, the answer given is also C. Iron carbonyl FeCO5 is mononuclear because there is only one metal atom, but the answer given here is actually incorrect. Answer given for this question 105 is actually A, okay, tetranuclear, which is completely wrong. Tetranuclear means you should have 4 metal atoms. Next is in black and white photography, the developed film is actually AgS2O3, so option number A here. Next, here is matching the following chlorophyll, okay, it is having magnesium, so one is C, that is this one. Blood is having hemoglobin, which contains iron, so 2D. Wilkinson catalyst is having rhodium, so 3A, and 4 is cobalt, okay. So option number B is the correct answer, but the answer given in the answer key for this question is also incorrect, okay. So that the answer here given is actually B, okay. Sorry, given is C answer is given, which is incorrect. Next, moving to question number 108, it is used for the hydrogenation of alkenes, okay, to give you alkanes. Next, we'll do filling the blanks question. The number of groups bound directly to the metal carbon is called as its secondary valency, okay. Number of groups directly attached is secondary valency. So this is your option number 1. The dash valencies are normally ionizable. The primary valencies are ionizable. Spatial arrangement are called as your coordination polyhedra. Dash dissociate into simple ions. Potash alum will dissociate into simple ions. In coordination entity, the central atom are referred as Lewis acids as they absorb electrons, okay, they receive electrons. When a ligand uses its 2 or more donor atoms simultaneously to bind a single atom, then it is a chelating ligand, okay. Ligand which has 2 different sites but either of the 2 ligands, that is ambidentate ligand. Coordination number of central atom is determined by the number of dash sigma bonds, okay. Dash complexes do not show geometrical isomerism, that is actually homoleptic complexes, okay. Next is facial and meridional isomerism is shown by octahedral complexes, okay, Ma3B3 type. Next is the example of the polydentate ligand here is EDTA. In a coordination entity PTCl-En2 dash isomer shows optical cis isomer. Linkage isomerism arises in the coordination compound containing ambidentate ligand. Dash theory fails to explain the bonds in the coordination compounds. That is our uh, bonds in the coordination compounds have directional properties. sp3d hybrid orbitals have trigonal pyramidal shape. Okay, I forgot. Dash theory fails to explain the bonds in the coordination compounds have directional properties. That is Werner's theory. Okay, so secondary valency very well explains that. Werner's theory postulates that but cannot explain. Next is set 4 here. CO, okay, CONH3 whole 6 3 plus forms a dash octahedral complex diamagnetic. NiCl4 2 plus is a dash complex. It is a sp3 complex, right? Or we'll see the options. Yes, dash is an inner orbital complex. COCN6 is an inner orbital complex. The oxidation state of nickel here is 0. Okay, hybridization of NiCN4 is dsp2. Okay, next we have set 5 that dash ion can bind through 2 nitrogen and 4 oxygen, that is your ethylene diamine tetraacetate. NiCO4 complex dash and diamagnetic, right? NiCO4 complex is tetrahedral but it is diamagnetic. Fex 3 minus has a paramagnetic moment of dash and paired electrons. Okay, so if you see it has Fe plus 3, that means D5 configuration, so there will be 5 unpaired electrons. Okay, so it is 5, that is option number 3. Next, MnCl6 is an outer orbital dash complex. So Cl is a weak field ligand, so it will be a paramagnetic complex. According to spectrochemical series, iodide ion is a weak field ligand. Okay. Next is question set 6. In high spin complex, D4 has T2G3 EG1 configuration. In crystal field, the subscript G is not used for tetrahedral complexes. In a complex having D1 electron absorbs lights with energy blue-green region, then complex will appear to be violet. Okay, next, dash theory attributes to the color, that is your crystal field theory. Removal of water on heating gives colorless compounds. Next is ambidentate ligand is NO2 minus. Vitamin B12 is a coordination compound of cobalt. Oxidation state of nickel is 0. Chlorophyll contains magnesium. Okay, next. Okay, so these are the top MCQs and I hope that there is a lot of error in the answer key, so please refer to this video properly, check the answers once again and then only decide. Do not just trust the answer key here. Okay, thank you so much, all the best, and I hope all of you have completed the challenge. Do let me know in the comment section. Bye bye and take care.